just barely not enough in, or too much one thing, or like outside elements like baking at a higher altitude.
Good.
Like there's different things in the environment and other things. So that's why you'll test it multiple times to like get an average or whatever.
I liked how he used the word, have a smiley face for that, Austin, how he used the word, we put it into practice. So far, we've only been doing things on paper. Paper is purely theoretical, right? It just says, based on the numbers I have, how much should I get? Okay? Actual, where do I have to go to find my actual yield? I have to do an actual experiment because you never know what's going to happen until you do it, right? You don't know what you might mismeasure or what your lab partner might spill, or possibly it's just a difficult reaction and they don't bond very well. And so even though you're meant to get this much, your actual is what comes out of it in the end. Okay? I heard some people talk about the word yield. So it's kind of interesting, as many words do. It has two different meanings, right? In driving, yield means to slow down, look for others, right? In this case, yield is referring to the product being made, right? I do an experiment and I yield my product, okay? For example, once again, a cookie recipe might say it yields 3 dozen cookies, right? If I follow this recipe as is, that's how many cookies I should be able to make, okay? The theoretical yield, once again, highlight this word, comes from stoichiometry. Okay, if a problem says find the theoretical yield, it's just another way of saying, hey, do the stoichiometry and tell me how much you should be able to make. The idea is why it's theoretical, because it's based in a perfect world situation. And when it comes to the real world, we're not perfect and a lot of things can go wrong. Or maybe you're like me and you really like cookie dough and so you eat most of it before you bake them. Because, that's why I make cookies, is because I like cookie dough. Okay? But keep in mind, it's all about theoretical, comes from math, because even if you don't want to admit it, math is perfect. We're not perfect as humans. We mess math up. But as itself, math is perfect. Things don't get broken. Things don't get lost when you do the math.
So it's not to say we didn't do the math wrong.
Yes, you might do the math wrong, but the math itself isn't. But then on the reverse side, the actual yield is what you actually end up with in real life. Okay? It is always less than or equal to the theoretical yield, and it's based on lab data. So today we're going to learn about these things in practice, a little bit more with the theoretical, but then on Friday we're going to go into the lab so we can actually create something. We're not doing cookies, but we are going to make silver, which is pretty cool too. You don't get to eat it, but it's pretty. I know, I'm sorry. I know Region swims on Friday.
Are we doing the gold too?
No, just silver.
Is that gold? You just have to reheat it, right?
Oh, we're not doing the penny one.
Oh,
It's a different one with silver. Yeah. So, some reasons why our lab data might not give us 100%. Okay, once again, our spilling, overflowing, overheating, dirty glassware. It also could be possibly maybe the equipment you used was inaccurate, right? There's also possibilities in that some reactions are just really complicated and it doesn't react fully even if you measure them out as best you can. Obviously, the goal as a scientist is to maximize percent yield, which is the ratio between the two. So this is what we're going to practice calculating today. Okay, a percent yield compares what you actually get versus what you should have gotten. It's a way of measuring the success of a chemical reaction. And I guess I shouldn't say so much a chemical reaction, more actually a lab process, right? Your percent yield measures how successful you were in the lab. When I was in college, so in college, your science classes and lab classes are technically different, like credits. And so you get different grades for the class versus the lab. And in one of my lab classes, our grade was dependent on our percent yield each time. So we had to perform this experiment, and if we didn't get a high enough percent yield, then we were coming back the next day to try again because that was what your grade was. Okay? But getting over 100% isn't a good thing when it comes to percent yield. Anyone have an idea of why? Why would over 100% not actually be good in this case? Usha?
Because, like, you can't just, like, create matter out of nothing, so, like, obviously there's something wrong with, like, your equation. If there's
Very
more than
good.
you started with.
Yeah, like she said, you can't create matter from nothing. So I can't make more than what I should have. So if you have over 100%, something is wrong, right? You obviously have something mixed in with it that's not actually your product, right? Like in our case with making silver, we're making it from a copper solution. And so if some of the copper is still sitting there, mixed in with the silver, it's going to be heavy, but it's not actually pure silver. It's what we would maybe call a dirty drug, right? Where it's not actually a pure substance. So over 100% isn't a good case here, okay? The way we set it up is actual goes on top, theoretical goes on the bottom, and then to make it a percentage, we times by 100. You could almost think of percent yield is just like the way you figure out a percent when you take a test. Because to figure out a percent when you take the test, on top goes what you actually got. The bottom is how many you could have gotten if you did it perfect. So it's kind of percentage, you kind of relate that as the same thing, okay? Okay, let me do a little demo here and then we'll jump into this problem, okay? So I'm going to do a chemical reaction between this substance, calcium carbide, and water, okay? I'm going to do it inside this bottle. It's a little bit dirty because I use them just for this reaction and I just repeat them, okay? What I have up here is I have a 0.5 grams and I have a 5 grams of the same substance. We're going to do this reaction 2 times, okay? So here's what it looks like beforehand. I'm going to drop these into water and then they will create a gas, okay? Now, gases are really hard to, like, capture and measure, right? So if I wanted to measure, like, how much am I making? So we're going to do a unique way to measure how much I'm making because this gas that it makes is explosive. And so we are going to ignite it, and the louder explosion we get would tell us what? Yeah, the more gas that was made. So don't say anything out loud. But once again, this is trying to bring to life what we're learning here. I want you to make a prediction of which one is going to make a bigger boom. Okay? 0.5 grams and that's 5 grams. So they're same reaction, just changing the amounts. Okay, let's get some water here. Oh. Okay, so what I'm going to do to capture the gas as it starts to be created is I'm going to put a bandana on top of our bottle to trap it inside. And then I have a small hole in the side of my bottle that I can use to light the gas. Does that make sense? You got to make sure it's a good fit before we dump anything in. Okay, hold on, I left my lighter in the lab.
Oh.
There's tannerite?
No, I was kidding. I'm saying we need to buy Tannerite.
You can online.
I know, you can buy it on Tannerite.com.
It's kind of like belt and
I know,
zipper, but then it like
oh,
goes
that's
like
what I
really
tried
like,
to-
and like on it, it'll like.
My dad just got a house for a guy, and he has an indoor like training shooting range, and he has blade rounds and like real guns, and they shoot lasers. So it's like laser tag. Is that sick?
You have to be
In his
a
house.
Okay.
You can't, because you have to like, you have to buy a range, then you have to get the blanks.
His house.
Yeah.
You don't know
Not
him,
like
right?
part of it. That's so.
But it's cool.
Oh, which one are you talking about?
Who?
Like the club
My
one.
dad just did carpet for his
The
dad.
storage one?
Oh,
No.
you should become friends with
Yeah,
Yeah,
that's
I know.
That's cute, that's pretty cool.
And he has a
Yeah, I didn't know
trout
which
farm
one.
in his backyard.
Talking
Dude,
about
sounds
it
really
was
rich.
sweet.
Where is he?
Phew.
She was on
He
teams.
lived in
Thank
New
you.
York.
Where is he now?
Teams for like.
Outline.
Okay,
Like,
ready, everybody?
on the mountain.
Oh, okay.
Once again, there's not a whole lot to see. This front table might be able to see a little bit of our bubbling going on, but it's more so we're listening for the sound it makes. Okay? All right, so I'm starting with 0.5 grams. I've done 60 milliliters of water. I'll dump it in, cap it off. I'll let it bubble because we want the gas to build up, right, react all the way. So I'll probably count to about 20. I will give you a countdown right before I go if you want to plug your ears.
Is it like two loud? I might want to plug my ears.
That's up to people's opinions.
Are you gonna be plugging ears?
Nope, because I have to hold the bottle. So.
She like lets go with one.
Put your hands down.
Huh?
Put your hands down.
Oh.
9, 10, 11, 12, 13,
She's counting for hide and seek or something.
16, 17. Okay, 3, 2, 1.
Whoa!
Oh, that was a good one.
I could.
No. The ceiling's always been like that.
Uh-huh.
Okay, so that was 0.5 grams. So instead of dumping in 0.5 grams,
Oh.
what if I use 5 grams?
That'd be pretty loud.
It might be big. It's gonna be the Big Bang.
Restart the earth. Okay, I gotta put this in. So same amount of water, but now 5 grams. I want you to show me thumbs up if you think it's gonna be bigger, thumbs down if you think it will be less or equal to.
I feel like she is tricking us too. I don't know why. Chemistry's chemistry. It's like science is like, but it's also like just myself.
Is that an exhaust Mac?
No, it's just a normal, like,
Mac was like,
inlet valve. Alright, sorry, that's a little smelly front tables if you're smelling something. So same exact thing, except I'm adding 5 grams instead of 0.5 grams. Okay, show me your vote, everybody. Show me your vote.
I'm just going sideways. I'm going to say sideways.
Okay, somebody who's pointing up, tell me why. Where's my face? Someone who's pointing up, tell me your prediction.
You know what? There's more of an explosive substance, and I'm so confused how it could be less.
Okay,
Like, I don't understand.
so Kenzie's like, there's more in here, which we know from stoichiometry. If I start with more, it should make more. Good. Have us my face for sharing, Kenz. Someone else want to share? Caitlin?
I feel like with more, it needs longer to react because there's more substance. So we have to wait longer because it's
Okay. Good, like, connection to the reaction. Have us my face for that. Boston?
Micah said something interesting, and he said that maybe it'd be less because you need more water. Since you're doing the same amount of water, you need more.
So we're using the same amount of water in both, and so maybe though, even though I'm adding more of this, it's not gonna matter because I'm adding the same amount of water. Have a smiley face. Both of you can for sharing. Why do I need a bigger bottle, Rip?
So that it'll take a long time, so it'll be more built up in there.
So Rip says right now, if I use the same bottle, what kind of result do you think I'll get?
The exact same, because
Okay.
it's gonna be the same amount that comes out.
Okay, but because I'm using the same bottle, but if I had a bigger bottle, then it would work. Okay, have a smiley face. Zayden, what do you think?
I would say also like kind of the same thing, like it takes the same amount of time for it to react, I would think. You know what I mean? Like to create the gases.
Yeah.
The same.
You think it's going to be the same as the one before because of just time. If I count to 20, the same amount will have been made. Okay, any other thoughts? Okay. The answer is it actually doesn't even go.
What the freak?
So I can show you it, and we'll see lots of bubbles. So it is making gas, but it will not explode when I try to light it. Does anyone know? We're kind of hinting towards it, but I haven't not hit it right on the nose. Nathan, what do you think? Say it louder.
There's not enough oxygen.
In order for things to explode, you have to have oxygen. And what happens is it makes so much gas, all the oxygen gets flushed out of the bottle. So Rip was on it. If I had a bigger bottle, then I could do it. So. I don't have one handy to do so. But hopefully this is making sense, everybody. Once again, great discussion of trying to bring these things on paper, right, to life. Like they are real reactions, they're real things, and you have to take into account all the components that are needed. Okay? All right, let's try 2 problems real quick, and then we'll get our homework done. It's really short homework today. It's only like 5 problems, okay? All right, so this one says a reaction with a calculated yield of 12.20 grams, so I'm going to underline this, produced 15 grams of product. So what we need to recognize here is which one is my actual and which one is my theoretical. Raise your hand if you could tell me how I could know which is which. Sasha, what do you think?
I think the 12.20 is going to be your actual because it's a 7 even number.
Not a bad thought. Not a bad thought. Have a smiley face for trying. Raquel?
I feel like it's like 15 because it's like the product of it, you know?
So which one's my actual? Yeah, if I read it how it says, a reaction with a calculated yield. Remember, calculated yield is another way of talking about doing the stoichiometry.
So would there be something in there that should be in there?
Say that again. So yeah, we're going to get, so this one right here, label this everybody. This is my theoretical. Because then the other key word here is how it said it produced. Right? Produced would mean that was actually made in the lab, right? So the one in blue here, this is my actual yield. So then when I set up my percent yield equation, the actual goes on top and the theoretical goes on the bottom. Which Rip noticed right away, like this person did something wrong in the lab, because our actual is bigger than our theoretical. Which doesn't mean we can't find it. It just means our answer doesn't indicate that we did a good job. Yeah, Raquel.
When we're like writing the equation, do we always have to put the percent yield in front, or can we just like write?
No, you can just write it. I was just indicating that this is the equation for it. So we do 15 by 12.2 times by 100. And I got 122.95%. Which means, once again, is this like a success or a failure? Yeah, so over 100 on a normal test is good. But percent yield over 100 is not. Questions on my numbers?
That's a percent. Oh, that's a
Percent. Sorry if that looks funny. Okay, so some questions you'll see, you just have to decode and say, okay, here's my actual, here's my theoretical. The other types of problems you'll see on the homework are like this, where it says, when 45.8 grams of potassium carbonate reacts with excess hydrochloric acid, 46.3 grams of potassium chloride forms. Calculate the theoretical and percent yields of potassium chloride. So in our previous problem, it gave us the actual and the theoretical. But this time, we have to find the theoretical. Using, how do I find a theoretical? Stoichiometry. I was my face, Raquel, right? Now, we have 2 numbers here. Which one do I use to find my theoretical, Austin?
I'm going to use the 46.30 for this one.
Why would you say that?
Because it's asking for the percent yields of potassium chloride. So, wait, I read it wrong.
You're good. You just fixed yourself. I knew you would.
So, whatever the one you want to find
Good. So what is this then?
That's the
Yeah, this is going to be our actual yield. Like this is how much was made. So this other value, this is what I use. This is saying, hey, here's your ingredients. Figure out how much you should be able to make. So I'm going to take that 45.80 grams. Potassium carbonate is K2CO3, and that's what I'm going to start with. Yeah, Sasha. So the actual is going to be given to us because it has to be done in the lab, right?
Right.
And so when reading it, you're trying to pay attention to what was actually made. So some keywords are formed, produced, created. So since that 46.3 grams was formed, that's the yield I'm looking at. Some other context clues that you can look for is potassium chloride is KCl. Oh, that was supposed to highlight it. Okay, your yields are only on the product side.
Okay.
Where the thing you start with is always going to be on the reactant side. So that can also kind of help too, of like, well, what do I start with? You have to start with a reactant because we're trying to figure out how much product was made. Great question, Sasha. I have a smiley face for that. Any other questions before we keep going?
The yield is always no matter what product.
Yes, yield by definition is a product slash.
And then on these ones, when it says 2 KCl, it's just the 2 of everything.
For what part? The 2 right here?
Yeah.
So that's going to come in when we do our mole to mole step.
Okay, so that's, oh, so it's not K, wait.
Does that make sense? So what I'm going to do here, everybody, is we're going to do a 3-step conversion to go from grams of reactant to grams to product. Okay? So just like we did on the warm-up, I'm going to start by going from gram to mole. I then can go from mole to mole. So once again, this whole part is just review from what we did before. And then I can go mole to gram.
Hopefully we're done with this one, and that's it. It's not a bad one, but I just want it to move on. I like this one. I like it, it's just like so many.
It's a lot of
steps, and it's
steps.
like, wow.
It is a lot of steps.
Yeah.
Each single problem does take a bit of time, so.
I feel like it's easier not to have to rewrite things, like you have to guess. I feel like once you know, math is just so much easier.
I'm with you, Caitlin. My brain likes math. Okay, so then this is going to be 1. The bottom's going to be our molar mass, which I calculated, but I can't remember.
138.
What'd you get? 130?
138.2.
Thank you. Mole to mole is a 1 to 2 ratio. And then we got another molar mass, so KCl. I got 74.55. Plug that all into a calculator. Divided by 138 to 1 times 2 times 74.55. I got 49.4. Do you have a second witness? Thanks, Kenzie.
Well, that's because you round.
Okay, now do I circle this as my answer and move on with life?
No.
Good. What do I do with this number? Yep, so I'm going to write it up here because I'm out of room. So I go. Which one goes on top, actual or theoretical?
Actual.
Good. So 46.3 goes on top. This 49.4 goes on the bottom. And then times by 100. And
That's pretty close.
They got a 93.7% yield.
It's an A.
So I'd say they did a pretty good job, right? Like, that's a pretty good lab.
How, in your lab, how would you do it? You would have to pick your own chemicals.
No, they would tell us what we were creating. So they'd say, here's the reaction that you're doing. Make this substance. But then the way they did it too was a combination of measuring the percent yield and the purity of it. Because if you get a 90% yield, but it's not very pure, right, then yeah, so. Questions on this idea? Okay, we got about 12 minutes to start on the homework. It's not super long, so you should be able to get a good start. Once again, some of them you have to find the theoretical yield, some of them it just gives it to you.
You said 12 minutes?
Because it's Wednesday, right?
Doesn't it go to 8:50?
I don't think 55.
I don't know.
I always think it's 55.
I was like, wait, am I just, do I?
No, you're right. We got 6 minutes. But you can do one problem. One problem before the bell rings.
Do we need to get on for the
Yeah, you only missed the warm-up.
Which I'm glad, because I was following it.
we do we skip the sandwich?
Oh, skip the sandwich. Wait. Turn the page. There's one that says percent yield. That's the one we're doing.
Wait, are we making sandwiches?
We might go back